All right. Short little lesson on Chapter 13. Really a reminder because Chapter 13 was covered in AC2. But here we're talking about series RLC circuits and parallel RLC circuits. So just a reminder about series RCL or RLC. When we talk about X, or we talk about the reactance, reactance L and C cancel each other out. So X sub L minus X sub C with the two lines around it means the absolute value, because it's always going to be positive. So instead of saying X sub L minus X sub C or X sub C minus X sub L, depending which one's larger, we just use the absolute value there. But that gives us our total reactance for a circuit. And then we can add that in with the resistance using our triangle, our impedance triangle, to get the total impedance or total opposition to the current flow. And there it shows total impedance is the square root of R squared plus X squared. Okay. And again, a series circuit, it can be capacitive or inductive depending on the frequency. And there again, in electronics, we would try and find the point where X sub C equals X sub L as far as the frequency goes. With power factor and power factor correction, we cannot change the frequency. The frequency of the power line is 60 hertz. And so we have to find how much X sub C and X sub L we need to get them as close to that series resonance point as possible. And so, like I say, in electronics, we'd vary the frequency to get X sub L to equal X sub C. In the real world, we know the frequency is going to be 60 hertz, so we vary the amounts of capacitance to offset the inductance that's already there. Okay. And so here, we show a simple impedance problem, just as a refresher. And so, reactance, 5,000 ohms of X sub C, 2,000 ohms of X sub L. So we have 3,000 ohms of reactance. In this case, it is reactance, and it tends to be on the capacitive side. Then we put it into our Pythagorean theorem. We get 3.16 kilo ohms of total impedance or total opposition to current flow in that circuit. We can always figure phase angle, which again, pretty poor here with 71.6 degrees and 3,000 ohms of reactance. If we could add more, in this case, more X sub L to get that closer to the 5,000, our phase angle would improve greatly. So magnitude of the impedance for this circuit. So now we have to figure our X sub L and our X sub C. There again, much greater X sub C than X sub L. So subtract the two, we get 589 ohms of X. Pythagorean theorem for impedance. Using our impedance triangle, we get 753 ohms of total opposition to current flow. There again, not a very good phase angle in this case. We have 470 ohms of resistance and 753 ohms of total opposition. So we're getting quite a bit of opposition from the reactance. Again, when X sub C is greater than X sub L, now when we look at this, we increase the frequency, which, like I said, then brings our X sub L much larger, changes us to 786 ohms, but on the inductive side instead of being capacitive. And so, again, we need to remember that a little bit, because it's just as bad for us to overcorrect as it is for us to undercorrect. So we need to keep track of that when we're calculating. Very seldom do we ever calculate all the way to 100% on power factor correction. And Kirchhoff's voltage law tells us we can balance those things out. And ultimately, that's what we're looking to do, get them very close to zero input or zero contribution, I guess you'd say, to the circuit. And like we said before, resonant frequency can be calculated with 1 over 2 times pi times the square root of L times C. So here again, if we know the inductance and we know the resonant frequency, which we happen to know again is 60 hertz, we can figure out how much capacitance there should be in the circuit. So we're going to use these formulas a little bit differently nowadays. And so here, again, going back to our problem, using those figures, we can calculate our resonant frequency at about 196,000 hertz. How do I generate 196,000 hertz? Frequency generator, right, or function generator. Not practical for everybody to have function generators at their house to keep things balanced or at a business. We're going to use 60 hertz. And so here phasors, again, reminding us about our triangles. Move to a parallel circuit, so we can't plot an impedance triangle anymore. Parallel circuit, I always recommend you plot a current triangle. So, here they're showing current on the resistive leg of 12 milliamps, current on the capacitor of 22 milliamps, and current on the inductor of 15 milliamps. So then we can set up the grid and we can subtract again the 22 from the 15 and plot our Pythagorean, or plot our current triangle from there. Use our Pythagorean theorem to get our total reactive current. In this case, it'd be 12 squared plus 7 squared. Add them together, take the square root. We get our I total. In this case, I total is 16.6 milliamps. So again, you can kind of see it on the phase angle there. It's not incredibly out of phase, but we are paying for, in this case, we're paying for 4.6 more milliamps of power than we're actually using. So again, just a reminder of the way things are inside of the world of series and parallel RCL circuits.